Any science suggesting the existence of something beyond Earth has always been greeted with enthusiasm, wonder, and a renewed sense of purpose in the search for cosmic companionship. Humanity, across countless generations, has always been fascinated by the idea that we might not be alone in the universe, that somewhere, out there among the countless stars, there could be others, perhaps like us, perhaps unimaginably different, looking back toward our tiny blue world. The excitement and inspiration that such possibilities bring have fueled both our imaginations and our scientific ambitions. Then came a turning point, one so monumental that it electrified the scientific community and captured the attention of people across the globe. This moment arrived when the James Webb Space Telescope delivered clear indications of life somewhere in the vast cosmos. While scanning the deepest, darkest reaches of space, this extraordinary telescope, built to peer farther than any of its predecessors, detected something absolutely fascinating on Proxima Centauri B, a distant exoplanet orbiting the small red dwarf star Proxima Centauri. The data streaming back was unlike anything astronomers had ever seen before. What it observed were lights, distinct, organized lights, that bore an uncanny resemblance to those of terrestrial cities on Earth. These were not random glimmers or chaotic bursts but lights that flickered in patterns far too structured to be dismissed as mere natural phenomena. The discovery was nothing short of astonishing. These unusual observations raised a profound and thrilling possibility that an extraterrestrial city might exist on that distant world. The very thought of such a place, an alien metropolis illuminated in the night, sparked waves of excitement and intense curiosity among scientists, researchers, and the public at large. For scientists, the intrigue lay not just in the potential for life, but in the even more staggering possibility of intelligent beings who might be organizing their societies in ways we are only just beginning to imagine. Could these beings be using technology similar to our own? Or perhaps something vastly more advanced, operating on principles that still elude us? Could they be reaching out, sending signals in ways we have yet to comprehend? Looking at these distant, sitter-like lights, which are located an incredible 4 light-years away from Earth, NASA engineers and astronomers alike found themselves awestruck. They began to wonder, how long have these lights been visible in space? How long have they been shining there, patiently waiting for our technology to evolve enough for us to notice them? David Kipping, an astronomer at Columbia University, described the planet where these lights were found as particularly complex. This complexity, he explained, stemmed from the fact that unlike most rocky planets, which absorb sunlight and emit energy in the form of infrared radiation, this exoplanet seemed to behave differently. Its behavior was shaped by a unique and dynamic relationship with its parent star, Proxima Centauri, a small but highly active red dwarf star whose flares and radiation levels make it unlike our own Sun. This discovery, made possible by the extraordinary capabilities of the James Webb Space Telescope, underscored the critical importance of continuing astronomical exploration. The telescope's ability to capture and analyze infrared wavelengths played a crucial role in detecting the unusual behavior of Proxima Centauri B. Observing in the infrared spectrum is not just a technical feat, it's a window into otherwise hidden worlds, allowing researchers to study atmospheric conditions on planets far beyond our solar system. With this advantage, researchers now plan to continue using the telescope to probe Proxima Centauri B in far greater depth, focusing on its atmosphere and the intriguing possibility that it might be habitable. One of their primary objectives is to determine whether this planet's atmospheric conditions could support life. The James Webb Space Telescope is especially sensitive to infrared light, a feature that allows it to observe phenomena on Proxima Centauri B even during its nighttime phase. For many telescopes, detecting faint light in the vast darkness of space, particularly light that may be artificial in nature, is an almost impossible challenge. Yet the James Webb is capable of picking up even the faintest glimmers, making it the ideal instrument to verify whether the supposed city lights on the dark side of Proxima Centauri B are genuine or just a trick of nature. This capability is due to the telescope's ability to detect artificial light if it falls within a very narrow frequency band, far narrower than the broad spectrum of light typically emitted by stars. This precision allows scientists to isolate potential signals from exoplanets like Proxima Centauri B, filtering out the overwhelming brightness of nearby stars. And Proxima Centauri B is no ordinary planet. It has a dynamic, evolving relationship with its star. One of its fascinating traits is its potential to enter a tidal lock, a state in which one hemisphere of the planet always faces its star while the other remains in perpetual darkness. Many solar system bodies experience similar gravitational interactions with their parent stars, locking them into specific rotational patterns. For Proxima Centauri B, this could mean that one side basks under constant, intense starlight while the other languishes in endless night. Such a condition would create extreme environmental contrasts, with the day side potentially blistering hot and the night side frigid beyond imagination. The reflected light spectrum from such a planet would vary dramatically depending on atmospheric and surface conditions. As Proxima Centauri B revolves around its star, it experiences something akin to day and night cycles, though not quite like Earth's. The planet endures searing heat during its daytime phase and markedly cooler temperatures at night. These temperature swings are heavily influenced by the planet's composition. For instance, if Proxima Centauri B has no atmosphere, the difference between day and night temperatures would be extremely dramatic. Without the moderating effect of atmospheric gases or bodies of water such as oceans, the day side could warm to uninhabitable extremes, while the night side could plunge into deep, frozen hostility. This dramatic thermal variation has become a focus of intense study for astronomers, as it provides valuable clues about the atmospheric composition and geological makeup of Proxima Centauri B. The James Webb Space Telescope, with its advanced infrared imaging, is particularly suited to analyzing the planet's thermal emissions. From these observations, scientists can gather key information about atmospheric properties, such as whether the planet has a protective ozone layer, significant cloud coverage, or greenhouse gases that might trap heat. Interestingly, the telescope's orbital path around Earth coincides in such a way that it can make detailed observations of Proxima Centauri B's daylight and nighttime phases roughly every 11.2 Earth days. If scientists confirm that the planet indeed has an atmosphere, the next step would be to analyze its chemical makeup in greater detail. This would involve searching for life-supporting elements such as oxygen, water vapor, and methane, all of which would strongly suggest the potential for habitable conditions. Detecting these elements requires the precise study of starlight as it passes through the planet's atmosphere, a challenging task but one within the capabilities of the James Webb. Though the telescope excels at characterizing planetary atmospheres, its design also serves broader astronomical goals, such as studying the earliest galaxies in the universe and the processes of star formation. Nevertheless, it remains an adept tool for analyzing variations in the concentrations of critical elements like water vapor, carbon dioxide, and methane. While it faces limitations in detecting free oxygen, a key biosignature, it can still search for ozone, which indirectly signals the possible presence of oxygen and a stable, life-sustaining atmosphere. As scientists continue to sift through the immense troves of data from the James Webb Space Telescope, the search for distant worlds marches on. Every discovery, every fragment of new information, brings humanity closer to answering one of its most profound questions: are we truly alone in the universe? It is important to remember, however, that the James Webb can observe only a limited number of exoplanets, primarily those nearest to Earth. For more detailed atmospheric studies and to delve deeper into the mysteries of far-off worlds, astronomers are turning to next-generation ground-based observatories such as the Extremely Large Telescope, ELT, scheduled to begin operations in 2028. The ELT promises to provide an unprecedented level of detail about the atmospheric structures of distant exoplanets. By studying their surface temperatures, atmospheric pressures, and chemical compositions, the ELT could offer an even clearer picture of their potential to harbor life. In the meantime, the James Webb remains an indispensable tool in the study of exoplanets. Despite its inherent limitations, it continues to provide transformative insights into worlds beyond our solar system. Looking forward, researchers have ambitious plans for future space telescopes, aiming to develop advanced technologies capable of reducing or even blocking the intense glare of starlight. This would make it far easier to detect and study the faint light reflected by planets orbiting those stars. It's a bit like shading your eyes from the sun with your hand to better see what lies beyond the glare. Only here, the hand would be a precisely engineered device in space. One promising technique is the use of coronagraphs, specialized optical instruments inside telescopes designed to block out a star's direct light while allowing the much fainter light from nearby planets to pass through. By manipulating the light waves, coronagraphs dramatically reduce glare, revealing previously hidden planetary details. Another equally promising technology is the Starshade, a massive, flower-shaped spacecraft that flies in perfect alignment with a telescope tens of thousands of kilometers away. The Starshade blocks the star's light before it even reaches the telescope, allowing only the precious light from exoplanets to be collected. If successfully deployed, Starshades could revolutionize exoplanet studies, enabling astronomers to capture direct images of distant worlds and study their atmospheres, weather patterns, and even surface features in detail. Together with advanced coronagraphs, these tools could usher in a new era where direct imaging of exoplanets becomes not the exception, but the norm. Scientists hope such advancements will allow them to detect specific atmospheric components, carbon dioxide, water vapor, or even seasonal changes, that could signal life. The implications of detecting artificial light or atmospheric anomalies on a planet like Proxima Centauri B are staggering. It would mean humanity is no longer the only technological civilization in its cosmic neighborhood, forcing a profound re-evaluation of our place in the universe, not just scientifically, but also philosophically, ethically, and theologically. It would raise urgent questions. How should we approach contact? What risks might come from transmitting or responding to signals? What might alien societal structures, communication systems, or even biology be like? Yet, as thrilling as these possibilities are, scientists insist on caution. Astronomers stress the need for meticulous analysis, repeated observations, and rigorous peer review before making extraordinary claims. Natural phenomena, such as auroras, volcanic thermal emissions, or unusual mineral reflections, could mimic artificial light signatures. Given the limitations of even our most advanced instruments, skepticism remains a necessary guardrail in interpreting ambiguous signals from light years away. Still, the human drive to know persists. Projects like Breakthrough Listen tirelessly scan the skies for intentional signals, while institutions like the SETI Institute refine their methods for detecting narrowband radio emissions that could indicate intelligent life. As more telescopes like the James Webb and future missions such as LUVOIR or HABEX come online in the coming decades, we may find ourselves